So what we are actually discussing about the equation of this equation or the relationship between the signal rate, which is signal rate or baud rate, which is S, and the bit rate, which represents N. So S equal to N by R, right? Where we know that S is representing the number of signal in 1 second, or baud rate. N is the number of bit per second, that is the bit rate, and R is number of bit in each signal element. For example, in this case, we have R is equal to 1 because in each signal can carry 1 bit. So 1 bit per signal element. So R is 1. If you think about the N, what will be the N here? In this case, number of bit per second is 8. So now in this case, N here for this case, in this case, N equal to 8 because 8 bit per second. If you think about the S, number of signal element per second, we also have 8. 1, 2, 3, 4, 5, 6, 7, 8. So here S is also the same. In the second case, the small r is 2 because one signal element or each of the signal element can carry 2 bits of the data. So according to the rule, that number of bits per signal element is r. So now the small r is equal to 2 here. If you think about the capital N, that means the number of bit per second, because we consider this is a second. So number of bit per second is 16, so value of N is 16, right? If you think about the S, number of signal element in 1 second, the value of S is 8, because we have 1, 2, 3, 4, 5, 6, 7, 8 signal elements in 1 second. All right, that's why the value of S is 8. Fine. There is another nice yes.
Sorry, in previous figure.
Okay, so this is also the 5 bit rate and also the 5 baud rate. What actually I was going to tell you about, there is another relationship between these two is, look at here. It says that in analog transmission, all digital data, the signal or the baud rate is less than or equal to the bit rate. That means the signal rate or the baud rate will be always less than or equal to the bit rate. Let's prove this one first. What is the S and N here? S and N equal or less? Here in this case, first case.
They're equal.
Is equal, right? Here the value of S.
Because both are 8.
Yeah, both are 8. So value of S and N both are 8. How about here?
Let the baud 8 and means 16.
That means baud is less than the bit rate, right? So that is the proof. That is the proof. Like what it says, the signal or baud rate is less than or equal. So either it is equal or it is less than. Here in this case, either it's equal or less than the bit rate. So the baud rate should be equal like this, or should be less than like this, less than the bit rate. Right, so that is another rule, and that is true for every time. That's why they have said that in analog transmission of digital data, the signal or the baud rate is less than or equal to the bit rate, and that is the equation. Very simple equation. Fine. So let's look at two very simple math. So the math says that an analog signal carries 4 bit per signal element. So what is the value of 4? Here it says bit per signal element. That means this is small r. So the r is 4. So r is 4. And if 1000 signal elements are sent per signal, that means this is 1000 signal elements in 1 second. That means S is 1000. Right? So we need to find out what is the bit rate. Very simple. R equal to 4. S equal to 1000, so it is very simple to easily find out what is the N. So that is the N. This is another proof that number of S and the number of N, look, S is less, number of signal is less, number of bit is high. All right, so there is another proof, which is 4 times higher. The bit rate is 4 times higher. That means each of the bit rate, each of the signal can carry 4 bits. So that's why it's 4 times higher. All right, so there is another equation to calculate the R. There is an equation called R, which is this R is equal to log base 2 capital L, right? What is capital L? Do you remember? R is equal to log base 2 capital L. So what is capital L? Level of the signal. Yes, correct. What is the level of the signal? This is the level of the signal. Whatever you have just seen, this is the level of the signal. That means how we represent the data. If it is 1 or 0, we need to have two different way to represent this 0 and 1, right? So that is the level. Here in this case, we have 2 bits of data for each signal. That means there are 4 combination is possible, right? 0 0 0 1 1 0 and 1 1. So we need 4 levels to represent this data. So these are the levels. So that is represented by that represented by L, capital L. So the equation is small r equal to log base 2 capital L. We need it for the next this math. Look at what is the math is. It says that an analog signal has a bit rate of 8000 bps. So that is the value of N, and a baud rate of 1000 baud. That is the value of S. How many data elements are carried by each signal elements? How many data elements are carried by each signal element? That is asking for small r. First question. Second question is asking how many signal levels do we need? So it's actually asking capital L. So let's find out. Very simple. We know the value of S, we know the value of N. We just need to find out the R and L. Okay, R and L. Okay, let me switch off. Okay, R and L. So let's find out the R first. Okay, so very simple. S equal to N by R, that is the equation. So obviously the R will be N by S. So that is our number of bits per signal. That's why they have written, look at the unit. It says bit per baud. That means bits per signal. That means 8 bit for one signal elements. That is R. So whenever we know the R, the equation for, and we need to find out the L. Very simple. R is equal to log base 2 L. So if you do the normal calculation, it will be 256. That means we need 256 levels to represent this data, because we have 8 bit per signal elements. Okay, and we have S equal to 1000 and N equal to 8000. In that case, we need 256 different types of level like this. We have 2 levels only, we have 4 levels only. That means like this, we have 256 levels. Fine. Okay, remember this equation also to find out the R. So to find out the S equal to N by R, and R is equal to log base 2 L. L is the level of the signal. Again, another proof that look at the number of bits and look at the number of signal elements. It's 8 times higher. So the number of bits is higher and the number of signal bit is lower compared to each other. Fine? You understand? Any question? Any question?
Yes, sir.
No question.
Awesome.
All right. So then if you don't have any questions, so let's go to our original conversion tools or technique. As I said, that there are 3 types of conversion: amplitude shift keying, frequency shift keying, and phase shift keying. So the first one is the amplitude shift keying. Same picture I'm going to show you. Same picture, look at the picture. We have a digital data, which is 10110. We are going to convert it into the analog signal, and that is the analog signal. we know that this is a amplitude shift keying. That means by varying or by changing the amplitude of our analog signal, we are going to represent the digital data. Let me tell you again. By changing the amplitude of a signal, whereas other two things, for example, our frequency and the phase will be remain same in this technique, we are going to change only the amplitude. So by changing the amplitude, we are going to represent the digital data. And this technique is called amplitude shift keying because we are shifting the amplitude. Remember, in amplitude shift keying, the other two parameters, that means phase and frequency, both of remain same. All right. So look at this picture, same picture as I said. Whenever we have one, we assume that the amplitude is high. So let's just say high and low. Don't say zero. So high amplitude represent 1 and the low amplitude represents 0. So high 1, low 0. So if you use this technique, high amplitude and low amplitude, and then we can represent 1 0 1 0 1 0. So the technique is called amplitude shift keying. Okay, it is called binary amplitude shift keying because we have only two types of uh, amplitude, high and low. That's why it's called binary. Fine. Look at this picture. This is our digital data. This is our original data which we want to transmit. All right, this is our original data, and we want to transmit it. So let's come back. So this is our data. This is our digital data. All right, this is our digital data, and we know that whenever we try to send any data through any transmission medium, um, we need to have a carrier. So why we need to have a carrier? Oof. So why we need to have a carrier? So think about yourself. As I said, a bus. So whenever we want to go from, let's say, Dhaka to Chittagong, right? We want to move from Dhaka to Chittagong. There are several ways we can go from Dhaka to Chittagong, this journey. So we can go on foot, we can use a rickshaw, we can use a car, we can use a plane, we can use a bus, anything. So what will be the difference if you just using or if you just go by yourself on a foot rather than you're using a bus? So whenever you reach to the destination, you will be distorted, it will be damaged, it will take longer time, right? Rather than if you just use a carrier, let's say for example you're using a bus, so it will protect you and it will carry you from the source to destination, right? Similar way to the data communication, if you just send the original signal from sender to receiver through any media, your original signal is very weak. It cannot go that much far. So in some point of the journey, it will be distorted, it will be vanished, it will be so many things. That's why, very similar to our real life, we will have a carrier frequency which can carry your original signal to the destination. And this carrier signal is very strong signal, and it can protect your original signal from the outer noise and everything, so that you can send it to the receiving end. A carrier signal is very similar to our bus, train, car, or plane, which can carry us. Same way, the carrier signal also carry the original signal. In the transmitting end, it will add it to the original signal, which is called modulation. In the receiving end, it will do the opposite. It will remove from the original signal, which is called demodulation. Very similar to our situation, we get in the car in the source address, which is Dhaka, and we get off the car in the receiving address, destination address, which is Chittagong. Here, data communication, same thing. We add the carrier signal in the sending device to transmit. We remove the carrier signal in the receiving end, which is called demodulator. Fine. So whenever you are using the ASK, binary ASK, we mix it together we mix it, we mix our carrier signal and our original signal, mix it together, my multiplier, and then we have this kind of signal which is called modulated signal. So whenever you add the carrier signal with your original signal, the resulting signal is called modulated signal because we modulate it. We are using ASK, that's why look at the modulated signal. High amplitude, low amplitude, high, high, and low. That means it represents 1, 0, 1, 1, 0. Remember, in ASK, all two other parameters are remain same. That means frequency is same and amplitude, and phase is also same. All right. So let's go to the next one. If you understand the previous one, the rest of the two I don't need to explain. Now you will explain this one. This is the frequency shift keying, second type of modulation. So what do you understand by this? Look at the picture. Tell me, anyone? What do you understand by this picture?
Sir, in this system, we need to change the frequency, and for 1, we have the higher frequency, and for the 0, we have the lower frequency.
So how you identify is higher or lower frequency? So that means we can say that yes, high frequency means 1 and low frequency means 0. High frequency 1, high frequency 1, low frequency 0. Fine. So that is the frequency shift key. Okay, my next question is, can you guess why this is called binary frequency shift keying?
Because signals are presenting by 1 and 0 at lower frequency than the 1 and 0.
No.
But there is only 2 type of signal.
Only 2 types of signal, for example. Explain a little bit
There are
more.
only 0 and 1. One is high frequency, one is low frequency.
Yes. We actually have 2 different types, yes. We have high frequency and we have low frequency. We have just 2 combination, right? So yes, you're correct. Actually, both of you are correct in some extent. We have 2 types of data, high frequency for 1, low frequency from 0 for 0. So that's why we call it binary frequency shift keying. Fine. Okay. And again, same rule. The other 2 parameters, let's say amplitude and phase, both of them are same. So in frequency shift keying, other 2 parameters are same. Let's check this one. How about this one? Not this one. This one. What is this? This is binary phase shift keying, right? So what do you understand by this image? This is the third technique, by the way. Come on, tell me, what do you understand by this one? Again, look at the picture. Okay, look at the picture. In the meantime, I'll take the phone. Hello.
Maybe black
Hello.
color signal is
হ্যালো কাকে ফোন দিচ্ছেন আমার ডেলিভারি আসে কথা yeah, what is it
the black color signal is off.
don't think about the color, please think about the signal.
Phase difference.
Phase difference, so tell me more about it. What is the phase difference?
High signal, high frequency has 180-degree phase, and the lower signal is 0-degree phase.
Which one is high frequency and low frequency signal? Oh, remember, Remember, this is the phase shift keying. That means the frequency and amplitude will be same. Only the phase is changing, right?
Yes, sir.
So,
So the high frequency phase is 180 degree. The low frequency, this one, sir. Yes, sir.
okay, let me tell you. All right. So we can see that there are two types of signal here, two types of phase. Look at this one more closely. What is the phase of this signal? This signal elements. What is the phase? 0 degree, right?
360 degree.
This is 0 degree, right? This is 0 degree. So this is 0 degree phase. This is 0 degree phase. So this is one phase. So whenever it is 0 degree phase, we can represent it as 1. How about this one?
180. 180.
What is the phase difference? Huh? What is the phase difference?
So
Come
the
on.
point of high is 0 and low is 180.
You forget about the phase.
Sir,
Let-
180.
180. Okay, very good. 180. How about this? Okay, where is okay, today? Yes. Look at these two pictures. This picture is actually the first one. First one, this one. The first one is this one. This one. So this is the same as the reference value, right? This is the same. This is the same as the reference value. So the phase is 0. How about this one? The same thing. See, it's starting from here. It's starting from here. So what is the difference between this and this? This is 0 degree phase, and that one is 180 degree phase, because it's actually missing this part, half of the cycle part, right? Half of the cycle is missing. Half
Yes, sir.
of the cycle is missing here. So half of the cycle means 180 degree. So this one is 180 degree phase. Okay, so this is 0 degree phase, that is 180 degree phase. So we can consider that 0 degree phase is represent 1, and 180 degree phase represents as 0. Same as here, 1, 1, 0. Same question, why it is binary? Because we have two different types of phase, 0 degree phase and 180 degree phase. Fine. Understood? Any question? No? Why you are not responding, by the way? Either you are not listening to me or you are not willing to respond. Which one is the case?